Okay, so good afternoon to everyone. And so this is the first lecture of the Holography and Quantum Information course, which I will be teaching together with Jan Boer. So my name is Alice Bernamonti, and I work at the University of Florence. And so if you want to contact me, so this is my email. And you can contact me if you want to ask questions about the lectures, if you have comments, feedback, want to know more references, and so on. Okay, so before starting with the topic of the first lecture, let me first give you some general context. And so the idea also beyond this field. So in the more or less in the past 15 years, let's say the dialogue between holography and quantum information theory has been particularly fruitful. And in particular, it has offered a radically new perspective on fundamental questions in both holography and the field of quantum information, and actually even beyond. And so as you will see in this course, the key concept here is that of entanglement or quantum correlations, which we know essentially distinguishes quantum from classical physics. And so the study of entanglement and its measures, its dynamical properties, and so on, and we will see actually a selection of these notions has been particularly bolstered in the past few years by the possibility of actually using entanglement in quantum systems as a resource, so to perform quantum communication tasks. And in parallel, at the same time, it was also realized that these quantum information theory developments also allow to actually discover a very powerful connection between gravitational physics and entanglement itself. And so at least within the field of holography, and maybe also beyond it, this type of developments has actually led us to think that even the same notion of space-time geometry might actually be an emerging notion which arises from the entanglement structure of states in ordinary quantum field theories. So let's say the basic theme is that somehow entanglement is underlying even the same notion of space-time geometry itself. And so the idea of this course is to try and aim at introducing the basic aspects of this rapidly evolving field and developments. And so, as I said, this is structured in two parts, because clearly to arrive to these more recent developments, we first need to introduce the basic language and ingredients that we will use. And so I will take care of part one of this course, as you might have seen on the syllabus, which is on the website. And I changed slightly the order and topic that I will discuss, but okay, I will update the syllabus in the next days. So in any case, so today I want to start introducing the areaCFT correspondence itself. So this will be lecture one. And even though I say that this is like some basic background material, clearly this is very fundamental in its own as well, because it's one of the most active modern research fields. So we will arrive to the areaCFT correspondence or holography or gauge gravity. And to do that, we will follow I chose to follow the original Maldassina derivation, which follows directly from the study of D-branes, and which does connect naturally to what you have just seen in the string theory course of Carlo Maccaferri. Then, ideally in lecture 2, I don't know, we will see how it goes with time. I don't have a clear sense yet. So we will review some real background material. So we will view elements of anti de Sitter spacetime, so the two main ingredients of the correspondence, and of conformal field theories. And hopefully this conformal field theory review will be complementary to what you have already seen in the string theory course, which mostly dealt with two-dimensional conformal field theories. And then in the third lecture on Monday, which actually will be morning and afternoon, we will actually arrive to see a bit better how this correspondence is actually realized. And so we can map quantities between the two theories in the duality. And so we will see, well, some of the main entries which are functional to the following lectures of the so-called holographic dictionary. And so the second part, which will be taught, as I said, by Jan de Boer from the University of Amsterdam, will then deal with these newer developments. So you will first see the notion of entanglement and of entanglement measures in quantum information, then in quantum field theory, and finally in holography. And then this will allow to explain some of the interesting applications of these developments, both for strongly coupled field theories and for quantum gravity, and possibly and hopefully, if the time allows, to actually connect to some very recent developments and some progress which has been achieved in the resolution of the information paradox. And okay, so if there are no questions on the outline, I guess we can start and ask me questions at any time, of course, and I will also do as the other teachers and stop the recording at the end, and we can continue to ask more questions if you want. Okay, so let's start with, let's say, the derivation of the areaCFT correspondence from the physics of D-branes. Okay, so in the string theory course that has just ended, you have seen DP branes as p+1 dimensional objects on which open strings end. You have seen the spectrum of open strings on a single DP brane, on a stack of coincident DP branes, and also on parallel DP branes, and possibly more actually. You have seen what is the word volume effective action on a D brane or a stack of D branes, and you have seen what's their tension and what's their charge in superstring theory, and much more. So I want to come back to this perspective in a moment, but before we do that, I want to take a different look at D branes. So as we just said, D-branes are dynamical objects. They have a mass and they have a charge, at least in superstring theory. Well, type 2A and type 2B, which are the ones that are relevant here. And as such, we expect these objects to also deform space-time. And so what we would like to ask now is what is the geometry which is generated by D-branes once we let them back react on the space-time. So D-branes and space-time geometry. So as I said, so we are working in superstring theory in type 2A and type 2B or type 2B. And so D-branes are BPS objects, and they have a mass or a tension. Let me just remind you the expression. Well, the overall factor. in any case. So they have a tension, so they are non-perturbative objects, and they have the right powers of alpha prime to be a tension. And they have a mass, which is, sorry, a charge, which is equal to their tension. Because they're BPS. And so, so now we want to solve, or at least see what is the geometry which is generated by these solutions. And so these are extended objects, but in fact, because of their properties, they are very similar to the well-known Reisner-Nordstrom solution for black holes. And so because of Birkhoff theorem, we can actually expect that depending on the ratio of their mass over their charge, we might have different solutions. So, so if this ratio is above some critical ratio, we expect this type of solutions to generate some black hole-like solution. And since these are extended objects with p spatial dimension, we would expect a black p-brane solution. If this is below a critical ratio, we expect, as we know from black hole physics, a naked singularity. And finally, if this equals some critical value, we expect an extremal solution. And so, as we just said, since D-branes in superstring theory are BPS objects, we do expect to be in this situation and thus to find, to find them to correspond to extremal solutions. And so let's now see the explicit form of this extremal solution. And let's, for simplicity, focus on the study of D3 branes. D3 branes, which are the ones that we will use to derive the areaCFT. So for that, we consider the bosonic low energy effective action of type 2b, superstring theory. So type 2b supergravity dimension. And so we want to look for some static, extremal, p-brane-like solution. So this is a solution which will preserve then well, Poincare symmetry on the Boer volume. So let me write on the 4-dimensional Boer volume and rotational symmetry in the transverse space, the 6-dimensional transverse space. And its source is the metric, the dilaton, and the relevant Ramon-Ramon form, which is the C4 form of type 2b. And so these actually, so the equations of motions allow actually a consistent truncation in which we set the Karl-Ramon field to 0. So these ones appear in the following. So as I said, we look for a solution of the equations of motions, which comes from type 2b supergravity. So let me write explicitly the action, which we have already seen. So we have the, okay, well, we have the metric, the dilaton, and the relevant 5 form. So the relevant 5 potential, under which the brain is both electrical and magnetically charged, because in this case, this is self-dual. And, well, let me just remind you that by, alpha prime to the 4. And I just split the dilaton into its asymptotic value, which fixes the string coupling, and its fluctuations, which I've called phi tilde. Okay. And so actually, before we proceed, actually, let me remind you what is the regime of validity of this action and of the solution that we will work out from its equation of motion. So remember that the regime of validity is a small string coupling, which means small corrections from string loops, so that we are in a perturbative regime, and low energy with respect to scale set by the string length, so that we can only keep massless modes and neglect all the higher massive modes. And so in terms of the geometric solutions that we are looking for, these also mean that the Ricci scalar of the solution, which is mass dimension 2, has to be much less than that's 1 over alpha prime, meaning that the space-time curvature has to be low enough, and that then effectively we can treat the strings as perturbative massless point particles. And we often talk, and probably, well, surely you have seen it already, about taking just the alpha prime to 0 limit. And well, okay, since I will probably also say that, and so since this is clearly dimensionful, what we have to keep in mind is that we take alpha prime to 0 while keeping fixed the energy. So this is the regime of validity of the action and of the solution that we want to look for. And so the most general ansatz for a metric which is sourced by n coincident D3 branes is the following. So let me write the metric. So we have a Poincare symmetry along the world volume. And rotational symmetry in R6. And so the only thing that we need to determine are essentially these two unknown functions of the radial coordinate R, and this is a solution for n D3 variants that sit at R equal to 0. So if we solve Einstein's equation and then we impose the BPS condition on for the charges of the solution, so then we find the extremal black three-brane solutions. Which then have this function f to the -1 equal to h of r equal to a function that I will call capital H of r, which for the three branes it's simply the 4 to the 4. And I will say in a moment what this capital R is. Let me just write in the meantime also the dilaton solution, which in the specific case of D3 branes is constant. And this is particularly important because it actually allows to extend the solution for any value of the radial direction. If the dilaton was instead running, we could happen to actually leave the regime of validity of this solution, so the perturbative regime in which the string is much less than 1, for some values of the radial coordinate. However, for D3 branes, this is exactly constant, and thus we can trust the solution everywhere. And finally, for the Ramon form, we have the following solution. Along the brane directions. Okay. So coming back to this scale capital R, so well, the way to fix it precisely, and you can check it, try to check it by yourself if you want. So the idea is that you should first impose self-duality of the F5 form, so the exterior derivative of the C4, and then impose that by Gauss theorem that the three brane charge of the solution that we have just written is that of n D3 branes, meaning that indeed this extremal three brane solution is the back reaction of the n D3 branes on spacetime. So you should impose that the flux on the S5 should be indeed given by n times the charge of the single D3 brane. And so in this way, and I invite you to try, you can fix precisely this R, which is 4 pi G strings times n times alpha prime squared, one could guess just by on dimensional grounds. Okay, so this is the characteristic radius of this geometric solution. And so let's look at a bit more closely to the metric that we have found. So first of all, asymptotically, for R going to infinity, we have that this unique function which appears, h of r goes to 1, and indeed we find that the solution is asymptotically flat. Asymptotically Minkowski in 10 dimension. As we start approaching the D3 brane allocation, but still far, sorry, so for R still much larger than R, we see that the force correction is the following. So I must have missed a factor 1/2 actually. I'm sorry. Yes. Just check quickly. Yeah. So let me write it to be. So this is h of r to the minus 1/2. There is no confusion. Okay. So as we start approaching the location, we see that the first correction is of this form. So h of r. And so we see that this is precisely, as again, you can check easily, This is precisely the Newtonian potential of an extended object, which has 3 spatial dimensions in the space-time dimension. Okay, and then as we approach this critical, well, this value, the scale value R, what we see is that indeed the deformation of the spacetime due to the D3 branes become significant. And in particular, one can check by computing the rich scalar, let's say curly R to distinguish it, that this is indeed proportional to 1 over R squared. And so that this radius R, which appears in the metric, is indeed the curvature radius of the solution. And so coming back to the conditions that we had before, we see that to remain in the regime of validity of our supergravity, what we need is that is alpha prime over R squared must be much smaller than 1 to have a small curvature. And so by substituting the expression for R squared, this means that G strings time n must be much greater than 1, with at the same time, to be in the perturbative regime, G string much less than 1. And then finally, as we approach the would-be brane location as R goes to 0, H of R is R to the 4 over R to the 4. And then if we look at the geometry with the correct powers, what we find is the metric, the following metric. So this is ds squared, R squared, R squared, dx nu. So this is the 4-dimensional space, plus R squared over R squared, dr squared, plus R squared d omega 5 squared. Okay, and so the space-time metric that we find as R goes to 0 is that of ADS5 times S5, which is a completely smooth, non-singular geometry. And so the S5 factor is this part, as probably most of you know. And so let me make some observations about this metric. So first of all, the S5 factor has a constant radius R, so it doesn't shrink to 0 as it's well, as often happens as small r goes to 0. And it also coincides with the ADS5 radius. Also, the region R going to 0 is actually infinitely distant from the asymptotic flat region. Indeed, if we look in terms of the proper distance, the L, then we have that, okay, this log R is a constant. And so for R going to 0, the proper distance diverges. And finally, the final remark is that essentially once we have taken the back reaction of these D3 branes which were sitting at r equals 0, and we let them, back react on spacetime. What happens is that indeed the sources, so the D3 branes, have disappeared, and we are left simply with a smooth, regular curved geometry, which has n units of flux. So this was the flux on the S5. So it's particularly useful to visualize better this geometry, to use an embedding diagram in which we embedded in a higher dimensional spacetime. And so from the higher dimensional point of view, this geometry looks the following. So at r going to infinity, as we have seen, we have a 10-dimensional Minkowski. And then as we get closer to the location of the D branes, the spacetime develops in infinite rows. So as we said, r going to 0 is at infinite proper distance measured by L. And this infinite throat has an S5 section, which has a constant radius r. And in the r going to 0. And so in the in this infinite throat, as r goes to 0, what we find is this ADS5 times S5 geometry. And so this type of limit, r going to 0, is known as the near horizon limit. Because indeed r equals 0 is the, let's say, event horizon of this extremal solution in which the area of the horizon is equal to 0. Well, let me stress that this type of solution is very different from what we know, for instance, from Schwarzschild type of solution like Schwarzschild black holes, in which the event horizon is always at a finite distance from any point in space. But it's very similar instead to the also well-known extremal Reisner-Nostrom solution for black holes, in which similarly the spacetime develops an infinite throat and asymptotically reduces to the metric of ADS2 times S2. And okay, let me again reiterate that this solution is everywhere regular, even at r equals 0, and that the D3 branes have been, so the origin of the sources have been fully replaced by a curved geometry with flux. If we were instead to find again still a singularity, that would be an indication of a residual presence of sources. So once we have fully back reacted the solution, there is no singularity. Okay. So if there are no questions, I will continue. So this was the geometric descriptions of D3 branes. So putting everything together, we have arrived to two complementary descriptions. So let's first of all go back to the picture that you have seen in the string theory course. So there we have seen, let's say, D-branes in flat space on which open strings end. So for our situation in which we have a stack of n D3 branes, and then we have open strings which end on the D3 branes. And of course, we also have closed strings, and all these elements, so branes, open strings, and closed strings, they can interact. So for instance, a D3 brane can absorb closed strings, which then decays into open strings, which remain attached to the branes, or vice versa. We can have open strings colliding on the brane, which can then form a closed string and then can leave the brane, and so on. And so the other picture, which we have just seen instead, is of D-branes as solutions of type 2b supergravity. So in this picture, as I said, we have a curved geometry with flux on the S5, and there are only closed strings. So there are no more D-branes on which the open strings can end, so we only have a theory of closed strings. And so by consistency, these two descriptions, these two pictures have to be equivalent. So it has to be that A equals B. And in principle, this type of equivalence has to hold for all values of the string coupling and string length. So this is an equivalence roughly between an open string picture and a closed string picture. However, in this form, this equivalence, even if it's rather surprising, is not so useful. On the one hand, even though it is true that this type of picture is known for all values, in principle known for all values of the couplings, in practice it's often very hard to actually deal with it in practice. And on the other hand, for the picture B, we know that this is only valid in the, as we have said, in the alpha prime to 0 limit. And so the idea of Maldacena in 97 was to actually consider the low energy limit of this equivalence. That is to consider typical energies, E, much smaller than the scale set by alpha prime. So equivalently, as always, fixed energy and alpha prime going to 0 with fixed G string and N. And so let's see what happens to these two pictures in the low energy limit. So once we look at picture A, so let's start from the open string sector. So as we take this limit, as we know, in the alpha prime going to 0 limit, the massive modes of open strings decouple. And the dynamics of this ND3 brains is described by a supersymmetric gauge theory on the brain Boer volume with gauge group UN. So this is the theory that you have seen. And so from the open strings, we get n equal 4 superior mills with gauge group UN and dimensionless coupling constant G mills, which is given by G string. So G mills squared is G string. In the closed string sector, something very similar happens. So if we take the low energy limit, the massive modes decouple, and only the massless modes remain. So we only have a theory with gravitons, dilatons, and so on. And moreover, what happens is that the coupling of the closed and open string sectors and also the coupling of the closed strings between themselves is given by G Newton. And so G Newton instead is dimensionful. And so as we take alpha prime to 0, this goes to 0. And so essentially the gauge theory on the Boer volume decouples from gravity in Minkowski and from the other modes of the closed strings, and also the interaction between closed strings modes go to 0. And so effectively what we have is a theory of, let me say it schematically, is a theory of free gravitons and of the other massless closed string modes in 10-dimensional Minkowski. And so in this low energy limit, what we find is that we have essentially two decoupled sectors. So we have, on the one hand, a theory of free gravitons in 10-dimensional Minkowski and n equal 4 superior mills on the Boer volume of the D3 brains. So in 3 plus 1 dimensions. Okay, and so now let's look at what happens at picture B. So the ones in we look at D brains as solutions of type 2B supergravity. So first of all, since the geometry is curved, we have to be a bit careful on what do we mean by energy. So in picture A, when we say that we take the low energy limit, what we mean is the energy of an observer in Minkowski spacetime. And so in B, this corresponds to the energy of an asymptotic observer which sits at R going to infinity. And so if we want to connect this to the energy at a generic location R, so we observe going back to the metric that the local proper time, the tau, is given by h of r to the minus 1 alpha dt, and thus the proper energy, which I will denote E tau, at a radial location r, is given by h of r to the 1 alpha, 1/4, 1/4 E. And so E is now the, well, as before, is the energy of the asymptotic observer at r going to infinity. And so in the low energy limit, essentially we have two types of situations. So for locations R, which are much bigger than the curvature radius of the solutions, this factor h of r, if you remember, goes to 1. And so the proper energy is essentially the energy of the asymptotic observer. And so essentially in that region, what happens is that in the low energy limit, the massive closed string modes decouple. Instead, if we go deeper inside the geometry, so for R much less than R, if you remember, this goes like R to the 4 as over R to the 4. And let me write it in the next page. And so what we have is that the proper energy gets rescaled by this factor. And so if we want to send alpha prime times E squared to 0, this means sending E tau squared, not squared, R squared alpha prime to 0. And now if you recall the expression for the curvature radius, this means sending to 0 eta square, r square. So essentially, the alpha prime dependence drops down. And now in this region, the proper energy can be whatever, it can be high enough, provided that we take R small enough. And remember that we are keeping G string Mn fixed. And so what happens is that as R goes to 0, all closed string modes survive. That is that due to the gravitational redshift, essentially the asymptotic observer sees these modes as modes with energy that goes to 0, provided that they are sufficiently deep inside the trough. And so since in the R to 0 limit, we have seen the geometry is that of ADS5 times S5. Again, what we have is two sectors. So we have again a theory of free gravitons in the asymptotically flat region. And we have instead full closed well, type 2B string theory in ADS5 times S5 in the near horizon region, and again with the appropriate flux. And again, as before, essentially these two sectors are decoupled because the string modes which survive, they are very deep inside the throat, and essentially they have little overlap and interaction with the massless modes, which instead survive at infinity. And so, let's see, box. So again, so these are the two decoupled sectors in this picture. And so if you put everything together, and since, as we said, these two pictures agree and agree also in the low energy limit, and since well, one of the coupled sectors in both cases is that of a theory of the three massless closed string modes in Minkowski 10. So that led Maldacena in 1997 to conjecture that the other two sectors would be actually equivalent. So let me write it a bit better. So that n equal 4 superior means with one gauge group in 3+1 dimension with dimensionless parameters G and Mills and N would be equal to closed type 2B string theory in ADS5 times S5 with dimensionless parameters G string and R squared over alpha prime. And so, well, as you, I guess you know, so this is the first derivation of the areaCFT correspondence. And so here we talk of, well, ADS because it's a theory in ADS, and CFT because, as you have seen, n equal 4 superior Mills is a conformal field theory. So the coupling is classically and also quantistically dimensionless. So this has a vanishing beta function for all values of the coupling, so a line of fixed point, and so this is a conformal field theory. And so this is a very remarkable equivalence. It's an equivalence between a theory of quantum gravity and a gauge theory. Even if it's supersymmetric theory, it's a simple gauge theory on a fixed background. And well, it is still officially, let's say, a conjecture, so there is yet no proof of the correspondence, even though this has passed so many non-trivial tests that I guess it's officially assumed to be true by the entire community. And I guess this might be a good moment actually to take a 10 minutes break if I manage to pause. I guess it's here, not this pause share. Let's see. Okay, so I will pause the recording. Okay. So we'll keep the chat, but please, if you want to ask questions, it's much more efficient if you unmute your microphone and possibly turn on your video as to have some kind of interaction and just ask them directly, because I'm not sure I will be able to follow the chat while I speak. Okay. So we have seen the original derivation of the most famous realization of this areaCFT correspondence. And now I want to make a few more observations about the two theories that enter in the duality. At least, I mean, this won't at all be exhaustive. It's just meant to be some observations, the most important and the ones that we will need in the following, because ideally in the following we will abstract from specific realizations of areaCFT, and we will look for let's say for robust statements that we believe hold across a variety of dualities, but still we will keep these fundamental example as the main reference example when we would like to be more quantitative. Okay. So let me make some observation. So let me first start with some comments on closed type 2B string theory on ADS5 times S5. So I guess the first comment is that we don't know much about it, but we do know a few things. So the first observation, as we will also review, I guess, tomorrow, is that ADS5 times S5 is a homogeneous, maximally symmetric space of constant curvature. And the important thing is that the parameter R, sorry, I wrote it not clearly, R is, it captures essentially everywhere the space-time curvature. And so string theory in this type of background is characterized by two dimensionless parameters. So the ratio, as we have said, alpha prime over R squared and G string, or alternatively, well, alpha prime over R squared and G Newton over R to the 8th. Well, let me just remind you that G Newton is the string square, alpha prime to the 4th, and well, expression for R, we have just seen it. It's the string. And so one significant limit of this theory that we can take, and that we have already essentially taken, is the classical gravity limit. In which we take G string to 0 and alpha prime over r squared with 0, so that we are both in the perturbative regime, and we can treat the strings as approximately as point particles, and or equivalently, sorry, here we can also consider the G Newton over R8 to 0 limit. And so this type 2B string theory reduces to type 2B supergravity, to derivative type 2B supergravity, which is much better known. And so this is essentially the limit that we will mostly have in mind throughout the discussion that will follow, even when we will work with more general holographic theory, sorry. So the classical gravity limit will be particularly significant. And here, of course, another limit that we could consider is also the classical string limit, in which we instead take, again, G string to 0 as to be in perturbation theory, but we keep alpha prime over r squared arbitrary. And this is another limit in which something can be said, but I won't talk about it because it's not the relevant limit for, let's say, the quantum information developments that will be the subject of the following lectures. And so the other observation that I want to do, observation 1, is that the S5 factor is compact, while the ADS is not. And so, so actually it's often convenient to expand the 10-dimensional fields in spherical harmonics of the S5. So for instance, let's say for a scalar, which will depend on the ADS, sorry, call it R, and sphere direction, it's often convenient to decompose it in spherical harmonics. Let's denote MYL of the S5. And so effectively this produces, well, as you know, it's like a Kaluza-Klein decomposition and introduces a tower of massless and massive modes. Just to be sure, is this something clear to everyone? Or should I just write the 2 lines to show you? Yes, no, maybe. Okay. Sounds good. And so essentially by dimensional reduction on the S5, what we have is that gravity is effectively 5-dimensional. So in particular, we can just take the Einstein-Hilbert action, 10-dimensional, dimensionally reduced, and we get a 5-dimensional Einstein-Hilbert term plus matter. Well, so essentially, okay, I will just write it schematically. What we get it's a 5-dimensional gravity Lagrangian with negative cosmological constant and a matter Lagrangian. And so for this reason, we will in general talk about gravity directly in ADS5. So we will mostly forget unless when we need it, about the time-dimensional origin. And so still in this regard, last thing is that when we say that we are doing a string theory in ADS5 times S5, we do not mean at all that we are doing a theory of gravity on a fixed background. So what we mean by that is that what we are doing is that, so ADS5 times S5 essentially specifies the asymptotic structure of the space. So it essentially fixes the boundary condition for the theory of quantum gravity, which is dual to n equal 4 super Young Mills. And this is just an important point to keep in mind. Okay, and now let me come to the observation 2. So the other theory, so n equal 4 super Young Mills, 2 plus 1 dimension. So as I guess you have seen in Carlo's lectures, this is a much better known theory. Let's see. Well, let me just remind you so that the fields, we have the gauge potential, we have 6 real scalars. I guess you derived all these details, right? In the course of Carlo Maccaferri. Plus the supersymmetric partners, which are 4 Weyl spinors. And so the important point that I want to make here is that all these fields transform in the adjoint of UN, as you have seen. And so they are represented by Hermitian M by M matrices. Okay, well, on shell we have, no, I guess I won't write the action or many more details because I've seen, I guess you have seen all of them. The observation that I want to make in regard to the areaCFT is that these UN matrices can be decomposed in an SUN times a UN1 factor, which is proportional to the identity. And by this, I just mean that for any field, I can write them in terms of components on the generators of SUN plus a factor proportional to the identity for the U1, and that of course these generators commute. And so that essentially all fields which are proportional to the identity matrix will give vanishing commutators, and thus effectively this U1 part of the super Young Mills Lagrangian gives a free decoupled theory from the SUN factor. And so if we go back to the D-brane picture, this free U1 is essentially related, well, the physical origin is very clear. It's related to the scalar and to the vector modes, which describe the center of mass motion of the system of the N D3 branes, and which does decouple from the intrinsic dynamics which instead describes the relative motion of the brain system, which is instead given by the SUN factor. Center of mass motion. And so, so essentially, this is just to say that normally when you hear about the areaCFT correspondence, this is a duality with n equal 4 SUN, superior mills. And this is because we only keep the interesting interacting part, which is the SUN, and we neglect the center of mass motion degree of freedom. Okay, and so I'm being very brief about n equal 4 superior mills. The only other thing that I want to mention, which I think you have also already seen, is that there is also a global R symmetry. Which is an SO6, which rotates the 6 real scalars between themselves, or equivalently also the 4 supercharges. Okay, and I think we won't need much more, at least for now. Okay, so the other observation that I want to make, which from my perspective is fundamental, is that this is an equivalence between, effectively, as we've seen, between a 5-dimensional theory of quantum gravity and a 4-dimensional quantum field theory, which, as we will see, we can essentially think as being defined on the boundary of the anti-de Sitter spacetime. And as such, this correspondence realizes the holographic principle, which was, let's say, first developed by Toft and separately by Susskind. In 93 and 94. And from which also the name of holography. And so this is essentially an argument, let's say an heuristic argument, which follows from treating black holes as quantum mechanical objects. And so I'm not sure if you are familiar with this argument, but it's very simple. So I think that since we have time, we might see it together. So, so I will just review or explain the heuristic argument from which the holographic principle follows, and of which the areaCFT correspondence is a realization, although this principle is much more general. So the idea, well, one way to see it is to consider an isolated system which has some energy E and an entropy associated S naught, and let's say in asymptotically flat space. And so then let A, the area of a sphere, or almost a sphere, which encloses the system. And let, so this is our system, and then let MA, the mass of the black hole, which would have an horizon area which is equivalent to A. So MA is the black hole with event horizon area equal to A. So clearly, it has to be that the energy of our isolated system has to be less than the mass of the black hole. Otherwise, our system would have already collapsed and formed a black hole. So what we can do is that we can add energy to our system while keeping fixed the area of the enclosing region to obtain a black hole of mass Ma. So we can add an energy Ma minus E with A fixed to form a black hole of mass Ma. And now clearly by the second law of thermodynamics, it has to be that the final entropy, so the entropy of the black hole, has to be greater or equal than the initial entropy plus the entropy S prime, which we can associate to the energy that we have added. And so the initial entropy, it's clearly smaller than the entropy of the black hole contained within the same region. So with area or h bar G Newton. And so the maximal entropy that can be contained within a region of area A is given by the entropy of the corresponding black hole. And this is known, well known as the Bekenstein bound. And so in quantum statistical physics, as you probably know, the relevant notion of entropy is the von Neumann entropy. Which is minus the trace of rho log rho, where rho is the density matrix associated to the state of our system. And let me just do a brief recap in case you don't remember. So for mixed states, we write rho. So for a statistical ensemble of different states with classical probabilities Pi, we write it as a sum Pi states psi I, where of course the individual probabilities are non-negative and they add up to 1. And so when we want to compute in general expectation values of some observables, we do it by taking the trace of the density matrix and of the corresponding operator. And so for such mixed states, the von Neumann entropy can be just given in terms of the eigenvalues, and so we can just write it as the minus the sum over I, Pi dot Pi. Okay. So if we have now a d-dimensional Hilbert space for our system, then the maximal von Neumann entropy that we can have is that associated to the maximally mixed state, so the one which contains the least information, for which the density matrix is simply the identity over the dimension. And so the maximal von Neumann entropy is given by log D. And so, so if we have a d-dimensional Hilbert state for our system, or rather, if let's say the effective, in a way that I will specify in a moment, if the effective dimension of the Hilbert space of a system is D, of a system which is of course bound by a region of area A is D, then we have that log D has to be, going back to the Bekenstein bound, has to be less or equal than A over 4 h bar G Newton, or equivalently over the area over 4 Planck areas square. Sorry, not Planck area. And okay, so effectively, if we have a system, let's say, of spins, and 1/2 spin 1/2 particles, the dimension of the Hilbert space would simply be 2 to the n, so a finite dimension. In general, of course, even for a single harmonic oscillator, the dimension of the Hilbert space is already infinite. Let's say, but however, I mean, for a quantum system which has a finite number of degrees of freedom, we can still think that the dimension of the Hilbert space, so of the states which are accessible at some fixed energy, is finite. So in that sense, I mean that we can consider an effective dimension for our Hilbert space, effective finite. And by that, I mean all states within the Hilbert state space which are accessible at some finite energy for the system. And so in typical physical systems, like spin systems as we've seen, or harmonic oscillators, which build up quantum field theories, the number of degrees of freedom is essentially given by the logarithm of the effective dimension of the Hilbert space. And so if we put these informations together, what we find is that in a theory of quantum gravity, the number of degrees of freedom which are contained within a region A has an upper bound which is given by the area of the region itself. So let me write it down. So the number of degrees of freedom of quantum gravity system within a region A, which goes like the logarithm of D, it's bound by the area of the enclosing region in units of the Planck area. And this is very peculiar. And essentially what it's telling us is that, of course, this is true only in gravitational systems, and that within this system, essentially, we have a drastic reduction of the number of degrees of freedom. So, indeed, this bound is surely violated in non-gravitational systems where we know, as I can just show you in a moment with a simple example, that the number of degrees of freedoms or the logarithm of the dimension of the Hilbert space instead is proportional to the volume of the region itself and not to the area of its boundary. So just to give you a simple example, which might be obvious to everyone, if we just look at a three-dimensional lattice of spins, with lattice spacing A, then we have that the number of spins will be given by the volume over the volume of the unit cell. And so this we can just write it as the area over the squared times the length of our system over A, just trivially. And so in general, if we take the size of our system L to be large enough, we can easily make this to be much larger than the area over L Planck squared. And similarly, if we look at the dimension of the Hilbert space, which is given by, so it's 2 to the number of spins, so it's 2 to the volume over A cubed. So then the maximal entropy that we can have is given by the volume over A cubed times log D. So just the dimension, sorry, the log of the dimension, which again, if we take large enough volumes for our lattice, we can easily make to be larger than the entropy of the corresponding black hole. So this was just to recall that, I mean, in general, we expect the number of degrees of freedom to scale at most with the volume. And so that this drastic reduction is typical of quantum gravity systems. So essentially, the holographic principle states that in quantum gravity, a region of boundary area A can be entirely described by at most 1 degree of freedom per Planck area. So by at most A over 4 L Planck square degrees of freedom, which is 1 degree of freedom. And so essentially what we have is that a theory of quantum gravity somehow secretly lives in less dimensions than those of the observed spacetime. And this is a consequence of just looking at black holes as quantum macroscopic objects. And as we said, it's realized in the areaCFT correspondence, but in general, we expect it to be much more general and profound. Okay. So if there are no questions here, I will go to the fourth observation that I wanted to do.
Sorry, actually, yes. I have a question. So what you mean by the fact that this principle can be violated in non-gravity system is that as soon as we approach a quantum gravity region, let's say, we have some sort of transition from a volume low and an area low.
Well, no, not really. I mean, what do you mean as soon as we transition to a...
Because you say we are assuming that that this is a system in which gravity plays a role, right?
Right, and it plays a role quantum mechanically. Yes. So,
okay.
so any theory of quantum gravity that we want to formulate, we need to satisfy this constraint. That's what I mean.
So maybe it's just philosophical my point, but gravity is always present, right? Shouldn't we always
yes, okay, of course, but I mean where its effects are non-negligible. Yeah.
Okay. So that's what I was trying to say. So
yeah.
Are you saying that when we don't when the effect of gravity are negligible, then we have a bound provided by the volume formula, and then as soon as gravity is
right, when quantum gravity
to be considered, we have some sort of a sort of transition to an area law.
Right. So that's the physics from the, from the physical point of view, and then from the consistency of the theory point of view, if we want to formulate a theory of quantum gravity, this is a constraint that we have to keep in mind, let's say.
Okay.
Yeah.
Thank you.
Thanks to you. Okay, and so now let me come to another observation that I want to make. So we have seen how to arrive to this conjectured equivalence between apparently very different theories. And then the next question, of course, is how is this equivalence implemented at the practical level? And so what is the dictionary between quantities, Hilbert spaces, states, and so on, between the two theories? So as I mentioned, we will see most of it on Monday. I just want to start here with very basic observations on the space of parameters of the two theories, which essentially just put together what we have seen so far. So manifold for superior means and in type 2B string theory. So the Young-Mills coupling squared is G string. So here I just want to tell you how the dimensionless parameters, or let's say recap, because we know it, they are related, and just relook at a bit better about the limits in which we are interested. So the N of the SUN gauge group corresponds to the N units of flux. Plus the S5. So in terms of coupling, I'm not sure if you have seen it in the string theory lectures. In any case, for this type of theories, a meaningful coupling in which we organize the perturbative expansion is the so-called Toft coupling, lambda, which is simply given by the product of GME squared and n. And so this corresponds to the ratio of r to the 4 over alpha prime squared. And well, similarly, the other ratio that we looked at, which was G Newton over R to the 8, corresponds to 1 over n squared. And here G Newton is the 10-dimensional one, but okay, similarly for the 5-dimensional G Newton. And so we are mainly interested, as we said, in the classical gravity limit. Because it's the one which is bestly understood and in which we know how to perform computations. And also it gives us access to, well, we will see it in a moment. So in the classical gravity limit, in which we take G string to 0, or equivalently G Newton, almost equivalently G Newton over R to the 8 to 0, and alpha prime over R squared to 0, so that we have no quantum corrections from loops of strings and no string corrections. And so if we just look at the matching of the parameters, we see immediately that this corresponds to the large n and large Toft coupling limit of the gauge theory. And so what we see is that this limit, which is highly non-perturbative, so it's a limit in which we have a very large number of degrees of freedom. The number of degrees of freedom here scales with n squared. So we have a very large number of degrees of freedom. We have a very strong coupling. So this is a highly non-perturbative and non-trivial regime of the theory, and this limit is described by classical gravity. And so for this reason, since the duality indeed relates weak, well, a theory at weak coupling to a theory at strong coupling, this is referred to as a weak strong coupling duality. And that's essentially one of the reasons for why this rephrasing in terms of a dual language is particularly useful. And so in particular, it allows us to address very, otherwise very hard questions for strongly coupled quantum field theories. And of course, we can work at leading order, or we can also compute, well, if we are computationally powerful enough, we can also compute corrections. And so quantum gravity corrections in G Newton over R to the 8 will correspond to CFT corrections in 1 over n squared, and stringy corrections in alpha prime over R squared will correspond to corrections in 1 over square root lambda. And so this is, as I mentioned, the limit in which we will be mostly interested. Another limit, which is sometimes considered in the literature, as we say, is the classical string limit. In which, so G string goes to 0, but we keep the ratio alpha prime over r square finite. And so this corresponds to the so-called Toft limit of the dual large N gauge theory. Large N, because indeed this corresponds to sending N to infinity, but working at finite Toft coupling. And I won't have much to say about this limit. I'm not sure, I think also Jan, but okay. But this is another limit which is often, or another regime which is often considered and can be studied to some extent. Right, so one thing that I forgot, okay, I'm not writing references. I will put the relevant reference. I put some already. I will put the main relevant references in on the web page, so you can just look there. Yeah, I'm just mentioning because I noted some references, but for the sake of time, I won't write them explicitly. Okay, so the ones that we have seen today is the best known areaCFT realization within string theory. Of course, there exist other realizations. So I guess you might already be familiar with some of them. So for instance, still within string theory, one can derive in along the same lines a duality between a superconformal three-dimensional theory, which is a theory on a stack of n M2 branes, and which is known as ABJM theory from Aroni, Bergman, Jafferis, and Maldacena, and which is dual to M theory on ADS4 times 7, or another well-known example is the one of the D1D5 system, which you might also already have heard, and which allows to derive a very useful ADS3 CFT2 duality. And well, I say it's very useful, I guess, because I have a bias for three-dimensional gravity theories, which are particularly simple, and two-dimensional conformal field theories, which, as you have seen, I mean, with the power of Spira-Soros symmetry, one can achieve a lot. But in any case, for the rest of these lectures, we will keep this D3 brane example as the main reference example. If you are interested in reading about other dualities, areaCFT dualities within string theory, I recommend the book of Armon and Ermenger, where there is a chapter which is well made and very clear and introductory about it. In any case, so as I was mentioning, we believe this duality to be much more general. And so the approach which we will take, which is the approach which is normally taken in the field, is to be somehow agnostic about the specific realization of areaCFT correspondence, and to actually try and look for statements that are valid across a variety of theories, so a variety of theories which are known or referred to as holographic conformal field theories. So here essentially what we will, so the basic assumption will just be that we have a d-dimensional conformal field theory, which is characterized by a strong coupling and a large number of degrees of freedom, and that there exists an holographic map to a theory of classical gravity in asymptotically ADS D+1 spacetime. So depending on what we will need to do, we might need to specify more or less details about this theory. In particular, I will mention some of the constraints that we know about the class of CFTs that are good candidates for having an holographic dual. But at the very, very basic level, we will just work from the bulk point of view with a bulk Lagrangian. So D+1 dimensional, so this is G Newton in D+1. And with Einstein-Hilbert gravity with negative cosmological constant and some matter Lagrangian, which we will specify the features that we will need depending on what we have to derive. And so essentially, at the crudest level, we just neglect all higher derivative corrections and work with this basic theory of classical gravity, where well, the cosmological constant is just related to the ADS radius in this way. And okay, so I think I will stop here. And so we will resume tomorrow by seeing the basic features that we need about ADS spacetimes and conformal field theories. Okay, so I think it's 2 hours. So I will stop the recording. I manage.